reactions involving gases. We've talked about how gases can be produced in chemical reactions. We can also have reactions that just occur in the gas state between different gases. And so we can calculate amounts of reactants and products using stoichiometry. There's just a little bit of a change in that we are going to use the ideal gas law to determine moles if we're given volumes, or to find volumes if we have moles. So if you're doing a problem and it says at STP, your life will be easier, because we know that at STP, 1 mole of any gas is 22.4 liters. And so that equation is going to be much simpler. And just be aware, you might also have pressures that are partial pressures, so you got to watch out for that. Here is our general overview for stoichiometry, which is mass, or grams to moles to grams. And so here we're switching up one or both of the ends. We can have pressure, volume, temperature of our initial gas, pressure, volume, temperature of the final gas. Let's do an example. In the following reaction, 4.58 liters of oxygen was formed at pressure equals 745 millimeters of mercury and temperature equals 308 Kelvin. How many grams of silver oxide decomposed? So this is stoichiometry. We're given information about one substance, and we're asked for something referring to the amount of another substance. And we have our balanced chemical equation. Let's use it to organize the data. So 4.58 liters of oxygen. So I'm going to write that over here under oxygen. 4.58 liters. And they're giving me a pressure, so that's N. They're giving me 745 millimeters of mercury. That's the pressure. There's no mention of collecting over water or anything. And this is the only gas, so we don't have to worry about partial pressures. Temperature is 308 Kelvin. And then the question, how many grams of Ag2O? So question mark, grams. Well, in the middle of every stoichiometry problem is moles. Moles of oxygen, the stuff we're given information about, to moles of what they're asking us about, Ag2O. This time they're asking for grams, so we're going to go to grams at the end. When we first learned stoichiometry, we would have started with grams of oxygen and converted to moles. But this is a gas, and we're given the volume, the pressure, and the temperature, so we can use the ideal gas law to find the moles of oxygen from the pressure, the volume, and the temperature. Okay, this is not N, it's V. So we're going to take PV and T and find the moles. Okay, I think we've done a lot of these, calculate the moles. So I'm going to do this in kind of a shortened version. So N equals PV over RT. So my pressure is given in millimeters of mercury. This is a shortcut that a lot of people use. Just do the division right in there, and then the unit will be atmospheres. If that bothers you, go ahead and do it how we've been doing it. Volume, 4.58 liters, divided by 0.08206 liter atmospheres per mole Kelvin. There's not really a shortcut for that. And then 308 Kelvin. So in my calculator, it goes 745 divided by 760, and then I'm going to multiply by 4.58, I'm going to divide by 0.08206. I'm going to divide by 308. And that gives me moles of oxygen. There's my moles of oxygen. Any questions? So now I'm here, and I'm just going to follow this using dimensional analysis, moles of oxygen to moles of silver oxide to grams of silver oxide. So I'm going to go to moles of silver oxide. I'll be dividing by moles of oxygen. And then I'm going to go to grams of silver oxide, dividing by moles of silver oxide. This is my mole ratio, comes from the coefficients. 2 moles of silver gives 1 mole of oxygen. And then I need molar mass, so 2 times the mass of silver, it's 107.7. 107.7 times 2 plus 16 for the oxygen, 231.4. Check my units, those cancel, those cancel. And I come up with 82.207 grams, 3 sig figs, so I'll report that as 82.2 grams of silver oxide. Any questions? Here's another one. How many liters of oxygen at STP are required to form 10.5 grams of water? At STP. Yes, we can use molar volume. So at STP means that 1 mole equals 22.4 liters for gases. So we've got 10.5 grams of water, and they're asking for liters of oxygen. So question mark, liters. So there's going to be moles to moles in the middle of this, moles of water to moles of oxygen. At the beginning, we've got grams of water, so that's kind of normal. And then at the end, we want liters of oxygen. And we can use this relationship because it says at STP. So this one's a lot simpler. So we're going to start with grams of water. 10.5. That's close. 10.5 grams of water. So I want to convert to moles of water. And then I want to go to moles of oxygen. And then I want to go to liters of oxygen. So I divide by moles of O2 here. And I divide by moles of H2O here. And I divide by grams of H2O there. Everybody okay with that? So I need the molar mass of water. You can calculate that. It's going to come out to 18.02. Mole ratio from the equation. 1 mole of oxygen gives us 2 moles of water. 1 mole of oxygen to 2 moles of water. And then this guy. 1 mole of a gas at STP occupies 22.4 liters. So we've got 22.4 on the top and 1 on the bottom. .5281 liters. So 6.53 liters of oxygen. Any questions?